nós vamos ter uma mesa redonda e eu vou convidar para compor a mesa os dois palestrantes, prestar algumas informações e logo em seguida a mesa será recomposta e eles vão fazer a apresentação de baixo. Então, eu convido o professor Mário para vir aqui à mesa, por favor. Professor Isao, Kubo. Então, eu vou dar algumas informações antes de nós ouvirmos as duas palestras. A mesa redonda leva o título de Estados Indisciplinados da Consciência. Esse título foi organizado a partir de uma conversa com o professor Marco Aurélio, que é o anfitrião do professor Brammer, e de uma conversa com o Rubem Cacheta, que é o anfitrião do nosso outro convidado, nosso catedrático, o professor Viegas de Castro. E nós não havíamos tido a oportunidade de consultar o professor Kubo. E por essa razão que nós colocamos como participação especial. Mas tão logo ele chegou e tomou consciência da proposta, ele aceitou de muito bom grado conversar sobre esse tema com vocês. Então, a mesa redonda, Estados Indisciplinados da Consciência. A ausência do professor Viegas de Castro resulta de recomendação médica. Ele vai estar sendo submetido a uma cirurgia amanhã, dia 2, e o médico o proibiu de ter alguma atividade estressante ou alguma atividade física mais intensa. Então ele teve que cancelar a participação dele. Mas ele tem um compromisso formal, diplomático, conosco, de que ele vai voltar para a última semana dessa primeira visita que ele nos faz no contexto dessa cátedra Fundeb e Arte Humanidades. Eu tenho o prazer de anunciar que o texto da palestra dele, que também se refere a estados indisciplinados, que ele proferiu há uns 15, 20 dias atrás, já está disponível no site, na página do IART. Localizar a página hoje é mais fácil do que achar telefone, lista de telefone. Mas de qualquer jeito é www.ufmg.br/IART. Então o texto está lá e o professor Rubem Cacheta e a equipe se comprometeram, já estão trabalhando nas perguntas e nas respostas que ocorreram durante a conferência. Então isso também estará disponível para vocês. Então essa com relação às informações com relação à mesa redonda de hoje. O professor Brammer, que já é nosso velho e caro conhecido, já é velho no sentido de que é a quarta viagem, é a quarta visita dele e a quinta visita para novembro já está programada. Eu estava observando, o Marco Aurélio, que é o anfitrião, já o chama de Miguel. Ele já está bastante brasileiro, né? Já se tornou brasileiro. Então ele é um neurocientista da Universidade de Londres e a apresentação vai se reduzir a isso, porque já é conhecido nosso. Então o professor Marco Aurélio já fez essas apresentações em momentos passados. E da própria fala dele, vocês vão conseguir localizar. O professor Isao Kubo é da Universidade da Califórnia e é a primeira vez que ele nos visita no contexto desse programa do IAD de cátedras Fundeb. e também ele é da área de Ciências da Vida. O professor Ribeiro de Castro é da área de Humanidade. Os dois que estão comigo nesse momento são da área de Ciências da Vida. E o quarto catedrático que nós temos no momento já aprovado pelos comitês, comitê científico, comitê diretor, e com a visita já organizada, é o professor Stuck, que é da área de Ciências Exatas, e o convidado pelo Departamento de Química, o professor FAFICH, professor Ribeiro de Castro, Kubo, o professor Isao, professora Maria das Graças, Brammer, da Faculdade de Farmácia. A trajetória dele é muito nessa direção de biodiversidade, e a grande conferência que ele vai dar, já então formalmente anunciada, no dia 9 de junho, quinta-feira, da próxima semana, às 9 horas, no Auditório da Reitoria, tem o título Potencial dos Recursos Naturais como fonte de novos medicamentos e cosméticos. Então, essa é a área de atuação, é isolando produtos e essências naturais, que o coloca como interlocutor, como catedrático do IAT. Estou vendo algumas pessoas ainda com etiquetinha aqui, me pediram para avisar, que a atividade do Congresso de Sociologia, programado para aqui, que seria GT1A, foi transferido para a sala de 3051, na Escola de Letras. Então, no dia 9 de junho, nós teremos a palestra do professor Isao Kubo, com esse título, no Auditório da Reitoria. Além disso, ainda também com a participação dele, nós estamos organizando um outro evento de uma forma genérica, para que eu não preciso voltar a isso. A grande totalidade, a grande maioria das informações que eu estou dando para vocês estão disponíveis na página do IAT. Toda a programação do professor Kubo está na página do IAT. Vocês podem, ele terá encontro com especialistas e ele terá atividades de natureza mais genérica, como essa que está aqui. Então vocês terão facilidade de ver qual é a programação dele lá. Mas então já dei destaque para a grande conferência semana que vem, e além disso nós estamos organizando uma mesa redonda com o título Alguma Coisa Parecida com, então falta definir a ser construída com os interlocutores, que é biodiversidade, conhecimento compartilhado e propriedade intelectual. Essa mesa redonda deverá ocorrer no dia 14 de junho. Vejam que então a questão da biodiversidade, conhecimento e propriedade intelectual, o professor Kubo vai poder falar com pertinência. Então é no dia 14 e além dele estará compondo a mesa o professor, senhor doutor Eduardo Emerich, que é o atual diretor da Biominas. Então, uma instituição com perfil de incubadora de empresa que também trabalha e tem o que dizer dentro dessa temática de biodiversidade, conhecimento compartilhado e propriedade intelectual. Os outros dois membros dessa mesa serão da casa, da FMG, professor Wagner Meira Júnior, que é do Departamento de Ciência da Computação e que é a nossa referência institucional, com interlocução nacional e internacional, da questão do software livre, então, o conhecimento compartilhado. E ainda na outra ponta, muito em cima dessa cultura popular do conhecimento, mais no sentido quase que folclórico das sociedades indígenas, do nosso sertanejo, dessas pessoas mais comuns na lida com essa biodiversidade, nós convidamos a antropóloga Manuela Carneiro Cunha, que é de São Paulo, uma pessoa que tem lidado com essa questão da propriedade intelectual do conhecimento sobre a perspectiva dessas sociedades outras que essa, meramente essa nossa hegemônica cultura ocidental. Eu já tive a oportunidade de compartilhar com vocês, mas quero fazer novamente, talvez alguém ainda não saiba. A questão de 15 dias, o IAT foi institucionalizado pelo Conselho Universitário. Então hoje nós fazemos parte da espinha dorsal da universidade. Nós hoje pertencemos, até essa data, desde 1999, nós éramos um projeto experimental com a missão de promover a aproximação das áreas do conhecimento, mas um projeto experimental ligado ao gabinete da reitora. Foi instituído, criado na gestão do professor César Sabarreiro e teve continuidade na gestão da professora Ana Lúcia, que nos ofereceu as condições para que esse assunto fosse ao nível do Conselho Universitário, e hoje fazemos parte da estrutura da universidade. Então isso é motivo de grande alegria para nós, e agora uma das consequências será a renovação do comitê diretor. Eu gostaria ainda de informar que em setembro estará ocorrendo o 2º Congresso Mundial da Transdisciplinaridade, que vai ocorrer no Brasil. O primeiro foi em Portugal, 10 anos atrás, e o segundo vai acontecer agora em setembro, em Vila Velha, Vitória, Espírito Santo. Informações também se encontram na nossa página. E a Eliana me solicitou que informassem as pessoas que tiverem interesse em um certificado de presença, para simplesmente assinar uma lista de presença. No final, isso será emitido para aqueles que tiverem interesse. Basicamente, então, essas são as informações. O professor Brammer está conosco a 4ª vez por 2 semanas, semana passada e essa semana, e o professor Kubo chegou nesse final de semana e já está nessa roda-viva de uma mesa redonda desse motivo. Nós o agradecemos de forma especial por essa disposição, mesmo não havendo um acordo prévio. E ele ficará conosco mais 3 semanas. No total, ele ficará 1 mês conosco. Sobrar a primeira vez com 1 mês é sempre assim. E esperamos que da próxima vez que ele fique 1 mês. Essas interações têm sido extremamente eficientes no sentido de promover as aproximações entre as áreas, entre os departamentos, entre os unidades. Nossa missão nesse momento é de sair para fora da UFMG e promover interfaces com outras instituições. Não vou falar sobre transdisciplinar nesse momento, essas são as informações básicas. Vamos então ouvir um pouco desses estados indisciplinados da consciência que estão muito bem posto, que começou com a palestra do professor Viegas de Casa na conferência. Foi acertado que quem falará primeiro é o professor Brammer, logo em seguida o professor Kubo, e aí nós retomaremos para as perguntas e os debates. Muito obrigado.
It's good to be here again in Brazil. Thank you very much for coming this afternoon. I have, I think, an advantage in multidisciplinary and transdisciplinary work in that the work that I do is, by its very nature, has to be multidisciplinary because I'm a neuroimager. I work on functional brain imaging. And functional brain imaging is more or less impossible without a group of people, without a team. So I'm quite accustomed to multidisciplinary work. And every time I come to Brazil, I think I have more interesting titles for talks to try to do. I think there's a competition between Yachi and me to produce the most difficult sort of concept to talk about. But, so this afternoon, I want to talk a little bit about some work that people have done in the area of consciousness using neuroimaging, a little bit about some of my own work with some of my colleagues, but also the work of other people. And really, all I want to do is to let those of you who are not familiar with this area have an idea about the kind of work that can be done, and perhaps more importantly, the kind of work that can't be done. This is a definition of consciousness from our most famous dictionary in England, the Oxford Dictionary. It says that consciousness is a noun, a substantium, and it basically is the state of being conscious, or one's awareness or perception of something. That is the definition of consciousness. Despite dictionaries having definitions like these, it's my experience talking about this subject to a number of people that if we go into a room full of philosophers and neuroscientists, we will probably get as many definitions of consciousness as there are people in the room. So it's a very difficult area. It's a very philosophically problematic area. It's a very neuroscientifically problematic area. And I don't think that I'm here this afternoon to answer any questions, maybe to put more questions than I answer. Okay. Some feel that there is a basic tension between philosophy and experimental science. This is quite a common view, and I think it's easy to understand this. That essentially, philosophers are interested in the fundamental nature of knowledge, reality, existence, and questions like these. We all may be interested in these questions, but we're not usually interested in them for a living, for our academic careers. Experimental scientists have a different view. Experimental scientists have the view that they may share many of the same goals. They may be interested in looking at the big picture, so to speak, but they're constrained by the nature of the experiments that they perform. In other words, as an experimental scientist, I can only answer the questions for which I can design experiments. So there is a bit of a tension possibly between the desire to have all-encompassing global theories and what is possible experimentally. And I think there's an interesting concept of what constitutes proof. I find this most commonly when I'm talking to my colleagues who are mathematicians. It's what they consider a proof. It's not really what I consider a proof. Philosophers, I think, resemble mathematicians in many ways. They're interested in global, absolute, incontestable truths. Whereas experimental scientists are only interested, or can only be interested, in truth insofar as it describes the results that they get. They cannot really talk about things which they've not obtained any experimental results. So their area of truth is essentially dictated, determined by the experiments that they can perform. Now, my basic question this afternoon, is there any common ground? This is the transdisciplinary bit of my presentation. Is there any common ground in issues or facts about consciousness that cross disciplinary boundaries and that are amenable to investigation in scientific experiment? This is where I come in. Let me talk in only 3 slides about neuroimaging. For those of you who are not familiar with neuroimaging, this is a very, very brief introduction. There are many different techniques for looking at brain function in vivo, and I think neuroimaging is broadly taken to be any technique which can examine brain function in vivo. Some techniques you may be familiar with, some techniques you may not be familiar with. The most common techniques these days are positron emission tomography, which uses radioisotopes, radioactive chemicals, to label different compounds in the brain, or in some cases to to study things like blood flow. Electroencephalography, which in many ways I suppose is the oldest neuroimaging technique, which measures electrical activity in the brain directly. Functional magnetic resonance imaging, which doesn't measure electrical activity at all, but simply measures the response of the brain's blood system to activity in the brain. In other words, functional MRI, which is what I work on, isn't a direct technique for imaging brain activity in an electrical sense. What we measure is the responses to brain activity by the blood system when the brain requires more energy. And there is another technique called magnetoencephalography, which rather more directly measures activity in the brain than either PET or fMRI. So essentially, you can divide these techniques into two groups. There are those groups that measure changes in electrical activity directly, such as MEG and EEG, and there are those techniques which measure changes in the blood flow associated with brain function, like fMRI and PET. And broadly speaking, the first two of these techniques are very good at finding events accurately in time, but not so good in space. And the second two are pretty good at finding events, localizing events in space, but not in time. This is an important point that I want you to remember, that there is no single very good or even approaching perfect method of neuroimaging. They all have compromises. They're all good at different things. This is a brief cartoon taken from an article by Nikos Logothetis in Nature a few years ago, just to show what goes on when there is brain activation. Basically, if your part of your brain becomes active, what is happening is the neurons in your brain are firing off action potentials, electrical impulses, and they're consuming energy. And the potential, electrical potential in the area around these neurons changes. And it's now thought that this, rather than what are so-called action potentials, is actually what leads to the signal that we measure in fMRI. What happens is there's an increase in blood flow following electrical activity. There's an increase in glucose use, and there's an increase in oxygen use. But the increase in oxygen use is a little bit less than the increase in blood flow or glucose. Now this is important because it means there's a little bit more oxygen hanging around the parts of your brain that are active than there would be if they were not active. And basically it's this that we pick up. It's this little extra bit of oxygen that we pick up when we do fMRI, which is what I do. And without talking about any of the physics at all, because it's not important this afternoon, I think, I'll just talk a little bit about experimental designs. Functional imaging experiments are almost contrasts between conditions. They don't measure an absolute level of brain activity. You actually measure the difference in brain activity when you change an experimental condition. And this is a very typical design. Here you've got an experiment which lasts for 5 minutes, and every 30 seconds you're alternating the experimental condition between two conditions. And these two conditions could be anything that you like. You could have more than two conditions. Basically, what we measure is the difference in brain response between these conditions. Okay, so that's another important thing to remember. Functional brain imaging doesn't measure absolute states, it measures changes in states in general. And here's another cartoon just to show you what fMRI data actually look like. This is a slice through the brain at about the level of the auditory cortex, which is around here. And this is the area of the brain that is responsible for dealing with sound, with spoken words, or with music, listening to music, things like that. And these images are taken 2 seconds apart. So you can see the sound was presented here. This is 2 seconds, 4 seconds, 6 seconds, 8, 10, 12, 14 seconds later. And you can see that there's a peak in the brightness of the image in these areas inside the brain about 8 seconds, 6 to 8 seconds after the sound was presented. And that's a good example of the kind of data you get from fMRI. It should be said, the brightness change here is very much exaggerated. In real life, you don't get change anything like as big as this. I've exaggerated it just to show you where it occurs. A little bit about the timing. So essentially, analysing functional imaging data consists of looking through a movie of brain images and finding those parts of the brain that show changes that correspond to an experiment. In statistical terms, you look for areas that are correlated with the experimental design in terms of their brightness changes. Okay, now that's a brief introduction to neuroimaging, and now on to the difficult bit, which is to talk about neuroimaging and consciousness. Now, at first sight, neuroimaging may be thought to be an almost ideal technique for looking at consciousness, because it basically can detect changes in brain function. So presumably it can investigate functional state. It can look at the neural correlates of these changes in functional state. So perhaps we could use it to look at ask some interesting questions in the context of consciousness, changes in conscious experience. However, there have been some very strong arguments against the whole idea that we can use neuroimaging to look at consciousness and to investigate consciousness. And I want to draw your attention, for any of you who are interested in this, to volume 8, number 3 of the Journal of Consciousness Studies, which is an entire issue virtually devoted to the single question of can functional imaging tell us anything about consciousness. And this issue started with an article by Revolso, in which he simply said, no, it can't. And then the rest of the journal, edition of the journal, consisted of replies by well-known neuroimagers, colleagues of mine in London in May, who replied to Revolso saying, oh yes, you can. So it's a bit like the famous, you can go to a circus. Oh no, you can't, oh yes, you can, sort of dialogue. So Revolso took the position that functional imaging is not very useful to tell us about consciousness. And then there were a series of refutations, if you like, of his position by neuroscientists who argued that functional imaging can. Now let me go through Revolso's argument. And I've outlined it here in the colour. Okay. Revolso's basic position was that he assumed that the level of organisation in the brain in which consciousness resides is a highly organised, macro-level electrophysiological phenomenon, realised by coordinated neural activity in specific neural populations. In other words, what we would probably say today, if we were at a neuroimaging conference, is a network of brain areas that are showing rapid dynamic changes in network connectivity. That is what Revolso essentially thought he understood by the neural basis of consciousness. And he proposed, as a result of that definition, that in order for a technique to be able to investigate consciousness, it would have certain properties. And those properties would be that it could measure accurately rapidly changing neural signals, neural responses across a group of brain areas. And Revolso's position was that none of the current neuroimaging techniques possess this sufficient statistical or resolving or experimental power for various reasons to address that question accurately. So Revolso concluded that because he thought the techniques were inadequate, the current neuroimaging methods, and this was in 2001, and things have not changed a lot since then, that neuroimaging techniques in 2001 were incapable, by their very technical limitations, of telling us very much about consciousness. And I think you can see the point that he's trying to make if you just go back to the slide that I put up about 3 slides ago, comparing EEG, fMRI, PET, MEG. Essentially, none of those techniques is perfect. They either localize well in space or they localize well in time, but none of them do both. Using the fMRI and PET, you can only localize a temporal change in the brain to within about 2 or 3 seconds at best. Using EEG and MEG, you can localize very well indeed in time, but the spatial localization is not very good. So Revolso's argument, which is at the core of many arguments made against neuroimaging, is that techniques simply aren't good enough to do the job. Okay, now Revolso reserves, he's very critical. It's an extremely good article because it succeeded in doing exactly what he intended to do. It got people like me extremely angry, which is exactly what a good scientific article will do. Especially as he managed to cite 2 or 3 of the papers that I've written to be examples of how not to do experiments, which I thought was even nicer. So basically, He reserved most of his criticism for fMRI, but by implication also for PET, positron emission tomography. Because he says that they fail because they simply can't localize brain activity within a time window better than a few seconds. So they're really not very good at looking at the rapid changes in neural activity that we know characterize changes in subconscious states. So basically, his final point, he made a lot of points, but this is his final major point. Brain images can be interpreted as showing that activated regions are somehow involved in the task, but they tell us nothing about how the task is done or what the activated area is doing. Serious criticism. Okay, now, there are several replies to Ramonsko's article in that journal. Two of them were written by people who also work in London, University College in London, at the Functional Imaging Laboratory of Queen's Square in London. One of them was a guy called Geraint Rees, and the other one was a guy called Christopher Frith. Christopher Frith is an extraordinarily eminent neuropsychologist. He's probably one of the best known experimental psychologists in neuroimaging on Earth, I would think. He's now a fellow of the Royal Society in England, which is about as high as you can go as a scientist. And I think the replies of Rees and Frith are quite interesting. Rees's argument, which I'll consider in great detail, I won't consider Frith's replies, because I think he said many of the same things that Geraint and Rees actually says. Rees makes the point that, okay, neuroimaging can't possibly tell you everything that you want to know about the consciousness. But if you design an experiment properly, it can be informative, and it can tell you certain things that might be useful. And he quotes two specific examples of experiments that have been performed. One on a phenomenon called visual extinction, and one on a phenomenon called binocular rivalry. Now, I'm presuming that many of you may not know too much about these things, so I will describe a couple of experiments that have been done to explain how these things are useful. Okay, so this is fine. This is just to summarize the position in response to Ramonsko's criticism. This is the position that Rees and Frith and many others have adopted. That is that functional brain imaging techniques can in principle be used to investigate some of the neural correlates of at least some aspects of consciousness. It sounds like a bit of a mathematical proof, making exclusion clauses all over the place, instead of narrowing down the field of investigation. So they don't make great claims about it being able to tell you exactly how the brain works, about how consciousness operates, but they do say that used properly with good experimental designs, it can tell us something that may be useful. Okay, the first phenomenon that Rees uses to discuss these issues is a thing called visual extinction. Visual extinction is an interesting neurological phenomenon. It usually arises in patients who have large cerebral infarcts, what in England we call a stroke, in the parietal cortex, which is this upper posterior region of the cortex. And following infarcts in the parietal region of the cortex, quite a lot of patients show an interesting visual behavior, and that is that when they're shown an object on the opposite side of the brain to where the infarct occurred, they have great difficulty in seeing it, or in recognizing that they've seen it. This is very important evidence. They have great difficulty in recognizing this, especially if you show another image on the other side of the brain at the same time. Okay? So they have difficulty recognizing the image, but they can do it. But if you show another image on the side of the brain, on the same side of the brain as the infarct, they have really major difficulty in recognizing it. Now, 2 or 3 neuroscientists realized that this presented an experimental opportunity to investigate at least one aspect of consciousness. This, by the way, is quite a common situation. If you look at the literature in neuroscientific investigation in areas like this, you will find that frequent lesion data on the behavior of people when they suffer cerebral damage in a particular area, is very, very useful for understanding more about the neurobiology of what's occurring in patients. And so basically, an extinguished visual field of stimulus in which the patient is unaware, this is the most important finding of all the people who looked at this, is still capable of producing activity in visual area V1, which is so-called primary visual Strangely enough and interestingly enough, the activity that's produced by the extinguished stimulus, i.e. a stimulus of which the subject is not aware, is identical to all intents and purposes to the activity in this brain region produced by a stimulus that the patient actually sees. In other words, there's no difference in the response in area V1 between a stimulus to which the subject is unaware and has no conscious recollection of seeing, and a stimulus to which the subject is aware and has conscious recollection of seeing. And this is the data to support that. Really all you need to do is just look at the top panel. And the only thing that are important, and my apologies to Mark, who is colourblind and always loves it when I make statements like this. The most important things are the blue line and the red line. And this simply shows that if they view the object on the same side of the brain as the opposite side of the brain, I beg your pardon, from the damage, they show a big response or reasonable response in the visual cortex in this little region here. But if the stimulus is extinguished by presenting two images in opposition on either side of the brain, they still show this change, even though they have no conscious awareness of seeing the image. Now, Rees says this is important because in 1999 there was a paper produced by Zecchi, who is an extraordinarily well-known visual physiologist, again working at the University of London, saying that on the basis of his reading of the literature, some aspects of visual consciousness reside in early visual areas, in other words, in areas that are to do with the early processing of visual data. Now, as far as I can see, and I will welcome many comments on this, the data that I've just reported, which is actually reproduced in several laboratories, would appear to contradict that, because it shows that in early visual areas, namely area V1, the conscious experience of seeing can be separated from the response to the retinal image, which is still being processed. So there's a separation here, apparently, between conscious experience of seeing an image and actually visually processing the retinal data. Now, I'm going to present most of the interesting work and aspects of conscious imaging. In fact, has been done on the visual system. So I'm now going to present another set of data from the visual system. This was reported in Neuron in 1998, and this concerns a phenomenon called binocular rivalry, which you may all be familiar with. This basically is if you show two different images to two eyes. For example, I think in the case of it shows the face of the building. The people will randomly switch perception between the two images. They'll report seeing either a face or a building, and they'll switch at intervals of a few seconds typically. This is a very well-known phenomenon in visual physiology. And this again looks to be a good target for possible work on conscious perception, because clearly, while these people are switching their perception of the images, the important thing is the images themselves are not changing. You're showing the same data, it's the perception that's changing, not the data. And you can compare that with what happens if you literally change the data. And this is the result of the experiment. So basically, here you can see the top of this slide. I think there's a stop working off here, which I think makes the other function. At the top of the slide, where it says change in percept, not stimulus, if you go over to the graphs, you can see there's a blue graph labeled FFA and a red graph labeled PPA. And the FFA is the area that's known to respond to stimuli like faces in the brain, and the PPA is the area that's known to respond to structures that are not faces, like, for example, buildings. And you can see that in changing in percept, you get a change, an increase in the blue line and decrease in the red line. And if you change back, the thing reverses. And interestingly enough, if you change the stimulus, you see the same thing. So here is an area of the brain which, unlike V1, is swapping percept when it swaps stimulus. So it's quite interesting. And here we have a change where perception seems to be localized in a higher part of the visual cortex, which is further through the processing stream, if you like, than V1, which is a very early visual area. In this case, percept. So in higher visual cortical areas, at the bottom, there's a summary of response follows percept, which is interesting. I'm showing these slides just to make a point again. The point that Reese was making in his defense against Ramonso is not that you can design an experiment to probe any aspect of consciousness that you choose to probe. I think that's impossible at the moment with the current state of technology and functionality. What these people have done is I think as with all really nice experiments, the art is in spotting some sort of a methodological change that will allow you to probe a particular phenomenon with some precision. And I think that's what these people have done. And I think the results can be criticised and are criticised, but they're interesting. Okay, and one of my colleagues, Geoffrey Gray, who's now dead, died a year ago. He's a great loss to neuroscience because he was, in fact, one of the most intelligent people I've known, one of the best neuroscientists I've known, had a lifetime interest in consciousness. And I owe my career to Geoffrey Gray because it was in 1994 that Geoffrey Gray decided that my institution should be doing functional imaging. So we actually bought a brain scanner because Geoffrey Gray said this was a good idea. So I'm here because of Geoffrey Gray. Geoffrey wanted to work on consciousness for virtually his entire life as a psychologist, but the tools available to him were, I think, inadequate, still inadequate at the time of his death. But when functional imaging arose, Geoffrey Gray jumped on functional imaging as a technique that he could use to ask some interesting questions about consciousness. And Geoffrey, I'm not going to say whether or not he shared his view, but Geoffrey was a great opponent of functionalism. And functionalism, I think, and for any philosophists in the audience, forgive me for this, because this is where the sort of fighting usually starts, is the thesis that a mental state's property of being conscious is one and the same thing as its property of occupying or playing a certain functional role. In other words, the property of actually feeling, being conscious of something is the functional correlate of performing that activity, I suppose, in some terms. In experimental science, it's usually phrased rather differently, and that is the theory is the functional organisation of the brain that produces or gives rise to consciousness. Both of these definitions are contested, but the question is, are they investigatable? Can we study them? Geoffrey, like the two people who designed the previous two experiments that I mentioned, was very good at spotting experimental opportunity. And Geoffrey's experimental opportunity was synesthesia. For those of you who are not aware of synesthesia is the phenomenon when a person can basically apparently produce a sensory response or a sensory percept by activating a part of the body that is not directly concerned with that sense or percept. A classic case would be somebody who hears colours associated with particular words. And we have a group of subjects at the Institute of Psychiatry in London who are so-called word and colour synesthetes. In other words, for some of these people, if you mention the word house, they always see yellow. Or if you mention the word road, they always see green. Or if you mention the word some abstract thought like sadness, they always see purple. I mean, they associate particular words absolutely reproducibly with particular colours. Geoffrey was a professor of psychology at the Institute, as I said, and he had a major interest in consciousness. And we carried out an experiment together in 2000 to 2002 to see whether we could actually get any interesting experimental results that might bear on the questions of consciousness using synesthetic predictions. Essentially, there's one major finding in this study, and that is that in synesthetes, unlike healthy controls performing the same experiment, when I say healthy controls, actually, I think synesthetes would probably kill me for that, because they would consider themselves unhealthy. So I retract that statement. So, synesthetes, unlike people who are non-synesthetic, on hearing words that they associate with particular colours, activate this area shown in red in the bottom left hand. Basically, the left hand brain image on the top row, which is labelled there V8. V8 is an interesting label because there's some differences between visual physiologists on how these areas should be described. The main thing is that this is the colour perception, or the colour response area of the brain. So if you do a very simple experiment where you show people coloured images and contrast them with black and white images, the area that comes up in contrast is this area. which is most commonly called V4. So the important thing is that synesthetes see or produce brain activity in area V4 when they're not seeing colour at all. They're simply hearing words for which they have a colour, following which they perceive colours. They are conscious of colours. So Jeffrey's point of view on this, which I'm quoting verbatim because he's dead and he can't possibly quote it himself, is basically the philosophical position is that conscious mental states can be distinguished by their qualitative properties and quality. And he maintains that the word colour synesthesia, apparently identical quality are associated with both seeing surfaces and hearing words. And this was published in Nature Neuroscience in 2002 by Julian Nunn and a group of us at the Institute of Psychiatry. And Jeffrey's take on that result was that it was a blow against the functionalist view in philosophy. Jeffrey then wanted to, if you like, to make that view firmer, and he studied another thing which is called the alien colour effect. And that is basically a rather strange phenomenon which is seen in a subset of people with synesthesia, which is that seeing one colour, they experience another colour. And it's been suggested that in these people, that the hippocampus, which is a part of the brain that's more commonly associated with memory than anything else, may be related to mediating the conflict between these colours. And in fact, when we studied people, synesthetic patients as subjects with the alien colour effect, we found that we could see variations in hippocampal activity that we didn't see in non-alien colour effect synesthetes or in control individuals. And Jeffrey wrote an article on this, which is just, I think, just this week been published in Cerebral Cortex, which is called Evidence Against Functionalism for Imaging the Alien Colour Effect in Synesthesia. And Gray argued on the basis of these two experimental findings that a similar colour correlate with different functional origins, as well as being functionally expressed in different brain regions. And he says that this may have a bearing on some of the current theories of consciousness, as they appear to be a single qualitative conscious experience from a fixed physical locational function association. So, this is just to show that we're still fighting about these things. This is the philosopher's reply by my reservations regarding the design of at least one key experiment in Gray's argument, but more importantly, the assumption that different functional roles may yield different experiences appears unwarranted. The same effect will surely be brought about in a law-like fashion by different causes. Furthermore, a functionalist could arguably allow one and the same conscious experience to play two cleanly separable functional roles, say in reasoning, one in motor reasoning, one in motor control and one in reasoning, in which case different functional roles would be associated with the same experience. So this is the argument getting more complex. So these are my conclusions from this brief talk about neurology and consciousness. Functional brain imaging is a new science. It's comparatively inexact science in many ways because we're studying quite small changes in the signals that we measure, and the signals are very noisy, so it's technically quite complicated. But we can study some aspects of brain function. Very few neuroimages would claim that we could ever think of providing a complete answer to brain function. One or two of my colleagues have actually said that using functional brain imaging will to understand how all your brains work within 10 years. I think those people are completely crazy, frankly, I have to say that. However, I'll be very conservative here. Functional brain imaging may allow us to probe some relevant questions in areas like consciousness. And it all depends, and I think Geraint Rees and Jeffrey Gray both made this point. The most important thing here is your experimental design. If you can design an experiment elegantly, concisely, properly to probe a particular question in an unambiguous way, then the answer may well be interesting. I think the problem here lies in what philosophers and neuroscientists would agree is an unambiguous way to do an experiment. So this brings me to the end of this talk. So one of the main problems for empirical research on consciousness seems to be the lack of agreement across disciplines concerning what constitute testable hypotheses in this area. This is a fundamental problem because unless we can agree on what we should be testing, we can't make any experimental progress. We can make philosophical progress, but not experimental progress. So what's perhaps needed is some sort of transdisciplinary consensus or consciousness about what's the ways forward. And I leave you with that thought. Many thanks.
not my mother language. Probably the person who is translating my English into the Portuguese may have a hard time, but I still have a very typical Japanese accent English. So that means easy for you to understand probably. The English I just listened to, that's the very typical English we call the King's English when I was a student, before you were born, most of you. Okay, this is a subject I was not really excited because the organizer asked me to participate in this symposium, round table discussions, but the subject is not my expertise. So, however, I'm getting that age to have to worry about the aging effect, something like Parkinson's disease, Alzheimer, and unfortunately we do not have good medicine. So I started this kind of the project about less than 1 year ago, and then I don't have answer. This is the medicine, but I have one message to young scientists or young students, because you learn something like this. You listen to the professor's lecture or a famous scientist's lectures. Okay, first, you should understand, try to believe it. Second, don't believe it. Okay? Particularly when it comes to the something which you are not totally agree. Okay, that's the time you can open up something, the next door, new doors. That's how I came into this Parkinson's disease project. Okay? The very fortunate subject I can start from Brazil. The Amazon jungle, there are about 10 mucuna plants. Probably you don't know, but very important plants they used to be. Okay? Because the seed of some mucuna plant contains even 10% dopa. But I'm going to show. But anyway, I'm a chemist. I cannot talk without the chemical structure. So try to learn, if you are not chemist, try to learn some chemistry, because I'm not going into the very deeply into the my specialty. Okay? And they give you some kind of idea. New Parkinson's disease medicine is coming, hopefully. I don't know, maybe next year or 10 years later, or maybe never. But I'm doing this project for myself. Okay? So, mucuna plant, I just started the mucuna plant seed contains the close to 10% of the dopa. The structure of dopa is if you're not chemist, don't worry about too much of the chemical structures. Dopa is this. This was used to treat the Parkinson's disease until 20 years ago. But now, because this compound has very strong side effect, then why this short side effect? That's the actual starting point. Okay? I just briefly explain this is the tyrosine, L-tyrosine. It's one of the essential amino acids you need every day, certain amount you get from food. And this is the important building block of the proteins, your enzyme in the living systems. This oxidized by the so-called tyrosine. Enzyme name is based on substrate and then produce the melanins. If you have this enzyme, everybody has it. Okay, you are the black hair colors and eye, skin, protections. That's actually important part, but also approach that age. The aging spot, sometimes is the old people get the spot like this, that is also melanin. And if you are not, you see the medical textbook, medicine textbooks, they indicate the skin cancer. The photo indicates something like black spot when the area where skin cancer develops. But that's actually my main source to get money to study cancer. Okay? So this is the substrate by this enzyme oxidize all pathway to melanin. So you got the idea what is the melanin. So you already have it. Oh, okay. I thought my voice is always large, that I have a glass like this and never use the microphone. Anyway, so I hope you understand the melanins. That many scientists working in this project. Okay, in space, the Parkinson's disease and the Alzheimer's disease, these two projects have big money. So everybody tries to get money, not really interested in the project, they work for money. Okay, so what they do is they look for dopa was once used as a melanin synthesis. I'm sorry, Parkinson's disease medicines. Anyway, so use dopa and this. Anyway, dopa oxidized to dopacnone by tyrosinase. And this reaction is very fast. Okay? And then the next dopacnone is almost chemically, not without enzymes. They reduce this. And they go to dopacnone. So from dopa to the dopacnone goes within 1 minute. Very fast. Okay? And the dopa is colorless compound. It's just like a white powder. And then the dopacnone is like a non-compound. So just like a color of the Coca-Cola. Okay? So you can see as soon as you mix dopa as a substrate and enzyme, like a solution, like a water, transparent water, that's go to the Coca-Cola pack. So you can see the reactions. And then, if you add chemicals which may inhibit this melanin synthesis, this is important. Anyway, they go to dopacnone and do it. Okay. So. Keyword, still you can see more than 10,000 papers. Many papers. Like I said at the beginning, many scientists, including very famous scientists, they made many papers. So we have to believe that first. And then I start saying that those experiments was good as initiative, but not enough. I'm not saying they're wrong, but we need to see from different angles. Okay? Because two important things are missing. From dopa to, you are checking only these reactions. In your immune system, substrate is the tyrosine. And then the product is the melanin. Okay? So the inhibition from the tyrosine to dopa, if your compound is inhibiting here, you don't see. Or your compound, testing compound is not inhibiting here, but if you inhibit the other part, you are missing. Okay, so that's the way I do have a kind of answer with several compounds, which could be good candidate to test the Parkinson's disease. Okay, so why DOPA is DOPA cannot use was used, but now cannot be used as a medicine to treatment of the Parkinson's disease. This is not the brain cell. We bought the brain cell from the HCC. But anyway, this is the prokaryotic model of the cells. But this is the Saccharomyces cerevisiae. It's a yeast, so has cell wall. Your cell does not have cell wall. Anyway, in brain cell, when you're getting older, I don't know how many years old, but you're getting older, the brain cells start developing or having it's not written here, but anyway, melanocyte. It's another organism, melanocyte, which contains pyrosinase, that enzyme I just mentioned. Okay, so the work we need to do it. I don't have enough time to explain why if you form melanin in the brain, it's a kind of the signal you are developing the Parkinson's disease. Okay, but that's the already published by many scientists. Okay, so we need to inhibit the melanin formation in cell of the brain cells, but do not destroy it without destroying the cell growth of the brain cell. Okay? Now, DOPA was once used from the Maguna seed, once used as a Parkinson's disease treatment, because structure is carboxylic acid. The DOPA cannot enter into the cell. Okay. This is I'm always cheating with microbiologists. They write the plasma membrane like just one line, and sometimes the textbook shows this. This is not molecular. This is the image. But anyway, I'm not arguing that. Okay, here we do have transporter. Remember, the plasma membrane is it's important part of selecting the nutrient taken inside, but the others not. Okay? DOPA is not the protein amino acid, not essential amino acid. So usually they don't take into the cells. So DOPA cannot go inside. There's still some scientists working with DOPA as a Parkinson's disease with the microcapsules. They put the DOPA, high concentration of DOPA with very, very tiny, but today's technology can do that. And then after surgery, put this micro capsule into the brain. So the DOPA coming very slowly into the brain. But that's not my subject. Anyway, so you need to take large amount of DOPA if you use as a medicine. Okay? Because it's not going into the brain, so it goes to other part of the body. And if you remember structure, it's a catechol moiety. That's easy to oxidize, so becoming very important the oxidant, destroy the other organisms. Okay, so that's before I start talking about the specific compound. Just keep in your mind why the DOPA cannot be used anymore, because it's highly toxic. Okay? And because it cannot penetrate membrane. That's the key. Now, back to this again. So from the DOPA to the DOPA clone is not enough to search for the melanin formation inhibitor. But this by essay is very simple, just like a 3 or 9. because as soon as you mix it, you can see change color. So just measure OD. Okay? But to form the melanin takes some time, and also for chemists it's not so easy to grow the specific cell lines. Okay? Now, however, we have to do it. They start using the tyrosine. That's the real substrate in your living systems, and melanin is a product. Okay? So I'm skipping the chemistry, but tyrosinase is a false enzyme, oxidase, isolated, because tyrosinase is not only humans, plants, microorganisms. If you see the black colored animal, that's all tyrosinase. Cat, if you have cat, black, that's the, melanin. Zebra, stripes, that's also melanin. Okay? So this is the model experiment we commercially available the tyrosinase from plants. Most important thing, isolated the protein or oxidase fast, long time ago, but the structure has not been established. Recently, a group of Swiss scientists confirmed the structure because they used animal, I think the unfiltered fluids. Okay, they brought skins and they isolated the tyrosinase. Fortunately, that tyrosinase is a single peptide, so all sequence of amino acid is established. Now, that's not the important part. The tyrosinase, almost all the oxidase relatives have metals, particularly divalent metals. In case of the tyrosinase, all doesn't matter, regardless of the source, as the copper. Okay? Other metal involved in this kind of reaction, iron, hemoglobin, something like that. The copper, this is the important active site. Okay, so this one is I'm approaching to the since we cannot use the dopa as the tyrosinase Parkinson's disease medicine, we'll just try to use one example, the medicinal plants I bought from Mexico. When I went to conference in Mexico, I went to the open market, and ladies selling this medicinal plants said, good for your brain. But I just, because she is not scientist, I asked, I want to be a good scientist. I need a good medicine for my brains. And she said, this is the one. Okay, but that's probably a joke. Okay, and then, but this is the not important because this is the main purpose we do for getting money. This is a simple molecule. It's very common from the food, even the spice, vegetables, avocado contain this. This compounds if you do this experiment, this compound that I'm trying to talk now cannot be tyrosinase inhibitor because this compound does not inhibit this substrate oxidized by the tyrosinase. Okay? But I'll give you the answer. This compound very strongly inhibits tyrosine to dopa. Okay, so to inhibit here, that's the reason why this compound inhibits the melanin formation, melanin biosynthesis. Okay, we did a lot of the biochemistry, organic chemistry to prove this process. That's the main part of my talk, but skipping those chemistry. If you're interested, I will be giving the similar, not same, but similar topics several occasions during my stay here this time. Okay? So coming to the several slide, skipping all those biochemistries. If you're really interested, you can ask me after my talks. I'm more than happy to show you. Okay? But I skip all the biochemistry parts and the results, the conclusions. Like I said, we just started growing the brain cells. We got the HCC, the human brain cells. But I'm not using the brain cells for students because they don't have experience. So use this is the mouse melanoma 16. This contains the melanocyte itself. This is a good model. Okay? And Albumin is a model compound because very similar molecules. This is commercially available and used for whitening agent. And in Asia, it's very common, expensive cosmetic product. Okay? Look at this, the design, the coumarin, pharmaceutical coumarin. This is 100 micromolar, inhibit about 20% melanin formations. But this compound, very simple compound, about 10 times less than standard compounds, and the study shows similar things. And then this is the one now being tested at University of California, San Francisco. Whether this compound really shows good medicine or not. I'm really hoping so, but we don't know yet. But that's kind of experiment we can do. The chemist can do. Okay? Now, I try to talk with something related to Brazilians. You drink the cashew or kaju, or eat kaju, right? And that's also maybe good source for Parkinson's disease. Because but anyway, remember I said the many papers published as a tyrosine inhibitor, okay, including us. However, many of them cannot be used as the Parkinson's disease because the main reasons. This is from Kaju. Just try to use this for conclusions. Right? This is the corridor. Some people I don't know, the mango is available in Brazil. I know some people in the United States or particularly Canada and Japanese, some people, less than 10%, have a program to eat mango, particularly mango export from other countries to Japan when it's young. They harvest the young, green one, not very mature. This still contains large amount of this carbo. This irritates the mouse. don't know I don't have this problem, but some people are sensitive to this. Okay, this is the reason why I explained that. That's the reason, because this kind of the head and tail structure is surface active compound, like soap, surfactant. So shows very good, very strong the tyrosinase inhibitor activity. Okay, but they also kill the cells. The many compounds tyrosinase inhibitor already published are cytotoxic. They're very selective compound which inhibit Mr. One important thing I will come back later. But this is still good because we try to develop the not longer in my hand, but they went to the commercial companies. Because this is the inhibitor tyrosinase. Then tyrosinase found almost everything based on those. So I don't know, the apple juice is not very common in this country, right? But the mangoes, apple, you have apples or avocado, you have the surface which they touch to the oxygen, which is another substrate, change color to brown. That's the same thing in melanin formation to the animals. Okay? So the apple juice, if you buy usually brown color because of oxygen, same reaction is happening. So if you mix mango juice, fresh mango juice and apple juice stay like water. Because of the tyrosinase, which called the polyphenol, same thing, inhibited by this compound. So cannot be used as the Parkinson's disease medicine, but the food industry, this is very interesting. Okay? But anyway, the most of the compound are known as tyrosinase inhibitor are toxic to the several levels. So last two with culture. Okay. This is not very strong tyrosinase inhibitor activities because you can see the millimolar levels. But the culture you eat, right? And this is we already published something, for example, the good antibacterial agent, helicobacter, against helicobacter. But not many medicines available for natural. But anyway, this is the compound found, a large amount found in cultured juice or cultured apple. When you eat or you drink, and these compounds also look at this. It's a very good melanin formation inhibitor. Remember I said I have to mention something very important. I'm very sleepy today. I don't know why. Maybe it's like. Okay, so these compounds, the paramethyl coumarate, the coumarate acid without methyl structure. You understand? Remember, this is the compound I'm talking. Okay, it's a good. You have methyl group here. Okay, but a natural source like avocado. Avocado is free acid, coumarate acid. Okay. When I show this kind of the graph, I forgot to mention coumarate acid do not inhibit the melanin formations because acid cannot penetrate the cell membrane. Okay? And anacardic acid, also acid, but it has a hydroxy group and also position. So make the intermolecular hydrogen bond. It's not real acid, so can penetrate the membrane, shows this activity. If really intersect the biochemistry, not happy to talk like artist meetings or come to other companies. I have to give so many companies. He knows how to push me. Questions we have questions.
Então, pequenos comentários transdisciplinares e abrir para a plateia. Obviamente que nessa altura a palavra do professor Viegas de Castro daria um toque todo especial. Nós vimos uma apresentação de técnicas bastante concretas, passam inclusive pela minha área física, que é de ressonância magnética. Então essa questão da funcionalidade e como isso pode ser levado a ser correlacionado com o fenômeno da consciência. Foi isso que o professor Brammer nos trouxe. E o nosso sonho, obviamente, e a título provocativo, como ele mesmo gosta de nos provocar e nós a ele, então foi Estados Indisciplinados. Então nós estamos na procura transdisciplinar dos Estados indisciplinados da consciência. Então ele já nos mostrou que essa correlação com a consciência já é um problema quase que intangível nesse momento, mas a nossa utopia, a nossa procura é um pouco por esses estados indisciplinados. E, de alguma forma, algum dia, algum momento, nós chegaremos lá. Então ele nos trouxe isso. O professor Kubo, obviamente, trabalha muito nessa perspectiva da correção. Veja, a natureza tende a um estado indisciplinado, no melanoma, no Alzheimer, em todos esses estados. Então, esses estados, e aí ele faz essa correlação muito na perspectiva da química, da bioquímica. Então, a mesa realmente agora estaria perfeita. Obviamente, o céu é o limite, nós poderíamos colocar os vários profissionais de várias áreas do conhecimento, mas esses três daria um toque maravilhoso aqui, no momento que o professor Viegas de Castro poderia nos trazer os estados indisciplinados do nosso comportamento, do pensamento selvagem, então, de uma forma tão bela ele trouxe para nós. Seriam três visões que de alguma forma nós poderíamos criar essas convergências transdisciplinares. Esse é o nosso objetivo, acho que isso estamos cumprindo. Então vou abrir para vocês, porque embora não tenhamos esse olhar pelo lado das comunidades, temos o olhar dos dois lados das ciências da vida, mas que eu colocaria mais uma da vida estrito senso, a neurocientista preocupado com uma técnica, procurando as correlações com os estados de consciência, e um profissional que eu identificaria mais como de ciências exatas, no momento em que ele trabalha toda essa bioquímica e correlaciona com esses estados indisciplinados da bioquímica, quando elas tendem a se degringolar, se degenerar para aquilo que nós entendemos como doença, mas vendo a morte como matéria-prima para a vida, resgatando toda essa indisciplinaridade e toda essa transdisciplinaridade. Então, o Marco Aurélio me provocou um pouquinho que precisava de alguém, eu propus ele falou, só se me desse tempo. Eu falei, eu também não, só se me desse tempo. Mas pelo menos eu tentei alguma coisinha aí, está aberto para que vocês possam formular as colocações de vocês, tanto do ponto de vista disciplinar, quanto do ponto de vista interdisciplinar, indisciplinado e transdisciplinar. E adisciplinar. Por favor. Então, eu agora vou ficar em pé para fazer trabalho de assessoria. Acho que vocês dois se organizariam com esse microfone e eu me silencio.
É uma pergunta para o Dr. Brammer. Você falou que tem algumas pessoas que são, não sei se em português seria sinestésicas ou sinestéticas. Sim. Sinestésicas, né?
Acho que é assim.
Que quando elas ouvem uma palavra, elas pensam numa cor imediatamente, né?
Mais ou menos assim. Mesmo.
Por exemplo, você fala house, aí vem a cor verde para ela, né? Eu queria saber se existe alguma relação semântica, de sentido entre essas cores. Por exemplo, se eu falo a palavra praia, se eu falo mar, se eu falo areia, se eu falo concha, entende todas essas palavras? Se seria a mesma cor para a pessoa, se tem alguma correlação.
Sim, essa coisa não acontece. Não tem uma relação desse tipo entre o som e o corpo. Não existe. I'm speaking English because it's easier. In some cases, you're right. There can be a semantic connection between there are obvious semantic connections. If we think of beach, we think of yellow. If we think of sun, we think of yellow. These people are not like that. The connections are not clearly obviously semantic. Not that we can deduce anyway. Now that would be a very simple explanation. There is an interesting bit of work. There's studies now appearing that what seems to be the problem in these people is that most of us don't have direct connections between the auditory cortex and the visual cortex in the brain. In some animals we do. For example, rats, I think, have direct connections. Some lower mammals have direct connections, but I don't think there's any evidence in human beings for a direct connection between the auditory and visual cortex. In these people in synesthetes, one of the theories is that they have a connection between the auditory cortex and area V4. So they have as part of their development, the wiring of the brain goes wrong. And basically instead of, an area that we don't know what it would normally be connected to becomes connected to area V4. So we think that that's the physical problem. If I can make a general comment about functional imaging and studies of conscience, I think one problem we have, all the experiments are basically at the same time. They're all asking the question, can we change some sort of conscious percept? And can we at the same time image what's going on in the brain? And it relies on the fact that when you're, the conscious percept, which is almost always by verbal report, is an accurate representation of conscious percept, if you like. So we're using, in both cases, we're using surrogates. This is quite a difficult area. We're using a surrogate, we're using functional imaging as a surrogate for brain activity. We're using verbal report as a surrogate for conscious percept. That, I think, is one of the problems in the experiment. Okay. So I think these experiments are not perfect, but the reason why people are interested in phenomena like synesthesia or the alien color effect or binocular rivalry or extinction is because at least it allows us to do experiments where the percept can be studied, changes in percept can be studied alongside changes in brain response. And we can either design experiments where there is no change in percept, but there is a change in brain response, like in the extinction case, or there is a change in percept and a change in response, like the case of binocular rivalry. But I don't think these are perfect experiments, but I'm just interested to see what people think about how close we may be getting to addressing issues of consciousness.
My question is more what you don't see in fMRI. If you get the same kind of activation in one specific area of the brain, that doesn't mean that the neural network is actually having the same dynamics, which means that it can be recruited, but it can have completely different dynamics. Now, if you can devise an experiment where different areas of the brain are recruited in specific awareness tests, then I agree, fMRI could be used to assess this kind of information. But if the same area of the brain is being recruited, and it's only being recruited in different temporal dynamics, for example, which has been shown by Zinger and other scientists, then fMRI, I would have to agree with the comments that the devil's advocate of fMRI that it would not be an appropriate technique to see it. So I'm actually more worried about what MRI does not see. But when you don't see difference, that doesn't mean that it's processing the signal the same way. It could be processing completely different, but would have the same oxygen consumption.
Okay, there's a very good reason why what you say is almost certainly true, and that is we all know that fMRI lacks statistical power. fMRI is a very, the signal is small, the noise is large, and the absence of a significant response never ever means the absence of a response, means the absence of a significant response. So you're absolutely right there. Where I think I am happiest, and I think I put the paper back in, somewhere on my computer. I can't remember which it is, but one of the two experiments I presented, I think is the binocular rivalry experiment. There was actually a patient where this person was undergoing surgery for epilepsy, I think, and they were able to implant electrodes in an area close to the visual faceform area and the place recognition part of the fusiform gyrus. And they were able to show that spiking activity in cells in those regions essentially followed the fMRI data. Again, I think that's not a complete answer, but it at least means we're moving in the right. I mean, obviously the problem with those experiments is you can't do them on those patients. They're completely opportunistic. You can only do them on patients where you happen to be able to do surgery, functional surgery if you like, at the same time. But I think they're interesting experiments because what they show us is not that if there is no, basically they don't show us, certainly don't show us that fMRI tells us everything, but they tell us that some of the things that fMRI is telling us about changes in percept and brain response are mimicked by work that you can do in terms of basic electrophysiology. And I have a problem with fMRI, and a lot of electrophysiologists have a problem with fMRI, and they're not quite sure what we're looking at. And I sympathize with that problem, but I think, even putting on my skeptical hat, which I wear most days, I think that the results from the fMRI experiments on binocular rivalry, extinction, and synesthesia, the alien colour effect, and some of the other ones that I haven't talked about, are at least interesting. I mean, for example, it's difficult for me, your argument would apply perfectly well to a negative result. For example, let's take a positive result. Let's take the work on visual extinction. It's very difficult to reconcile Zeki and Bartel's theory of consciousness, where they say that a lot of visual consciousness resides in primary, early visual areas. It's very difficult to see how that can be true in the case of that experiment where you completely divorce percept from visual response, and in that case you are detecting a response. And I've got a feeling that if you did the same thing with microelectrodes, you see the same thing. In fact, I think it's been done, but certainly the binocular rivalry experiments have been done on monkeys, and I think maybe extinction experiments as well.
Yeah, the binocular rivalry experiments that they did in monkeys, they actually do that bar scrolling. Yeah. So you actually have one sense that the bar is scrolling up, the other one that the bar is going sideways. In that case, fMRI would probably not see any difference. If you show the house in the face, then you are actually directing to secondary circuits what actually would be perceived as being a face or a house. Then good, because you're actually looking at other structures. But inside the same structure, these people have shown that in the primary visual cortex, you actually see differences in the processing of information. In the temporal, and you would not see that in fMRI, right? Sure. What I mean to say is, it could be activating V1 with the same blood flow consumption, but actually that would mean a completely different processing, even in those patients who had strokes in specific areas of the brain. We cannot guarantee that the adaptation of the neural network will actually be the same.
Okay, let me take your view, which I think I again, I agree with, which is that it's probably a mistake to characterize a neural response, even a fairly early visual response, entirely on the basis of one brain area. You should probably look at a lot of brain areas, because the brain doesn't work, the brain almost always works in networks. I mean, the sort of completely modular processing of idea of the brain is probably only true in maybe the visual system, the auditory system, and maybe parts of the motor system. It's not true for higher cognitive processing. We know that it's not true. We know that we're dealing with fluctuating networks. I mean, no, I agree with what you're saying. You know, if the idea came across that I think that fMRI is going to tell us how consciousness works, then you know, that's not what I intended. What I'm saying is that it can allow us at least to design experiments to start to address some of the hypotheses. That's all. There's one big problem with consciousness research. I think that if you adopt the position, I think that some philosophers adopt a completely what I call dualistic idea, that the mind and the brain are different entities, and that the mind is not a construct of any organic organization of the brain, and of course you can't investigate it experimentally very easily, and there we have a problem.
That's it.
Bom, eu queria fazer a pergunta, inicialmente, para o coordenador da mesa. Eu queria perguntar em que sentido o IEART considera que esse evento aqui é um evento transdisciplinar. Eu fico me perguntando em que o IEART pensa que seria diferente isso que está acontecendo aqui de outras situações em que o professor, o primeiro palestrante, poderia estar fazendo essa palestra no ICB e o segundo palestrante poderia estar fazendo essa palestra no ICES. No último evento do IART, eu já compareci buscando em torno do conceito de transdisciplinaridade. No final eu fiz uma pergunta que eu achei que não foi respondida e aqui de novo eu queria ouvir dos três participantes da mesa qual é a concepção de transdisciplinaridade. Por exemplo, o primeiro palestrante estaria sendo transdisciplinar porque estaria abordando com técnicas da fisiologia um tema que tradicionalmente é pensado como um tema psíquico. O segundo palestrante estaria sendo transdisciplinar porque está tratando com uma técnica da química um tema que tradicionalmente é da área médica, a doença de Parkinson. Então eu gostaria que a gente avançasse um pouco nessa discussão sobre o que é trabalhar transdisciplinarmente.
Naturalmente que eu vou me omitir de entrar nessa discussão, eu vou passar para os nossos nobres visitantes e eu estaria aqui 24 horas por dia para a gente poder discutir isso. A discussão sobre os fundamentos e a base conceitual da transdisciplinaridade por si só é uma discussão que eu acho que nós temos mais que aproveitar os nossos visitantes do que eu tentar fazer um diálogo desse com você. Mas o objetivo do IART é promover a aproximação, e a frase mais conservadora que nós ouvimos o tempo inteiro consiste exatamente nessa: o que o ICES não pode fazer, que é necessário o IART. O que o ICB pode fazer, que torna... o que o ICB não pode fazer, que torna necessário o IART. Essa é uma discussão que nós vamos discutir noutro fórum, noutro local. Nós temos aquele livro, Metodologias Transdisciplinares, Fundamentos da Transdisciplinaridade. Agora, a nossa visão é exatamente essa, de procurar as porosidades, as pontes, as interfaces entre as disciplinas. E se isso fosse percebível de uma forma muito clara, então realmente nós não precisaríamos da transdisciplinaridade. Mas vendo os dois, e o professor Viegas de Castro falando simultaneamente, obviamente que algumas pessoas inconformadas com a sua outra especialização disciplinar, inconformada com os limites que a disciplinaridade coloca, ela iria conseguir achar essas pontes, essas porosidades, essas ligações, essas convergências que é a procura que, de uma forma geral, todo mundo está fazendo hoje, para além da ultra especialização disciplinar. E é óbvio que é um privilégio ver duas pessoas, ICB e SEX, sentados na mesma mesa, dando o seu recado, e algumas pessoas aqui vão ler, apreender isso de uma forma diferenciada de que se o professor Brammer estivesse falando no ICB. Não espero, mas eu acho que eu até gostaria de ouvir o testemunho do professor Brammer, quantas e quantas vezes ele nos diz da experiência transdisciplinar que ele tem podido.
What is transdisciplinary? What is multidisciplinary? What is interdisciplinary? I can only have my view, which is why I decided to take part in this project. For me, there is a common situation in science where you get an expert in one field who advises a non-expert in another field and basically progresses the research in the second field. But the person who is receiving the expertise still is, if you like the English phrase, none the wiser. Has just received expert. It's like going to a consultant. You receive expert advice. It helps your research project. It gets you grant income. It gets you papers. But you're not really understanding or participating in the knowledge of the other person. You're receiving it in a sort of parasitic sense, if you like, rather than a symbiotic sense. What I think of as transdisciplinarity, and I may be wrong about this, is much more a symbiotic idea. And in fact, in my own career, I think one of the reasons why I decided to take part in this project here in the outsheet is because I started life as a biochemist, not a mathematician. And I became so interested in some of the mathematical ideas underlying biochemistry that I decided to acquire the skills in that area myself. And what I'm looking for now, across many disciplines, across geophysics, across macroeconomics, across biochemistry, across cell physiology, are concepts, ideas that are not confined to one discipline, ways of approaching problems, solutions to problems that are shared across multiple disciplines. So rather than just receiving expertise from someone else and not understanding it, I'm looking at central themes in research across areas that are consistent. I don't know if that makes things clearer, but that's my view of transdisciplinarity.
Sorry, I wanted to ask a question earlier, but I thought I was going to stop you using the right questions. Anyway, you talked about the case that some philosophers, they separate the brain and the mind. I think there was a guy called Steven Pinker who works at MIT. He calls it the ghost in the machine. You separate the brain from the mind. And what I want to ask you is, what exactly do you call consciousness? Because I was reading an article by a philosopher called Daniel Dennett. I don't know if you've heard of it. But for him, I think human beings would be the only animals that are truly consciousness. And according to the things I heard from you, it seems that consciousness is the same thing as electrical impulses. So I may be wrong. What exactly would consciousness be?
I don't think it's the same thing. I mean, maybe they are manifestations, different manifestations of this phenomenon going on in the brain. I have to say that I'm a bad person to ask to define consciousness because I've given up the attempt ever since I sat in a room about a year ago with a mixture of 50 neuroscientists and philosophers, and I think during the course of the morning we had something like 25 different definitions of consciousness. So I've got absolutely guarantee you the way I define consciousness would be completely disputed by every philosopher in this university and every other university. I think of it in terms of things like awareness and volition and control over actions, intention, that sort of thing, or a mixture of these things, my own view of it. But it's very difficult. In terms of the experiments that I've described, conscious awareness is actually defined very simply, isn't it, in most of these imaging experiments? It's defined in terms of what people report they've experienced, isn't it? That's basically what these experiments are defining as a conscious person. If you think of the extinction experiment, the person was asked, did you see this picture or not with your left eye? If they said yes, that represents a conscious percept of the image. If they said no, it doesn't. So consciousness in that narrow sense is defined as just a recognition that a visual percept, some sort of visual construct, has happened and been processed at a level of awareness. And you could argue that in the case where V1 has responded, that the person has not said that they were aware of it. Something has obviously happened in the brain. We know that V1's responded. We know there's electrodes in there, you can see V1, but the person has not recognised that that event has occurred. And so there is some sort of a point in the processing of it. You know, I'm sort of, if you like, a biological basis person, neuroscientist. There's some point in the processing of that visual information where it reaches a level where it becomes part of the construct, part of the reference of the human being to their surroundings. It becomes a recognised part of the environment, as opposed to that not being the case, which I guess is unconscious response. But I have to say that I've tried to study as many subjects as I can in my life, and I've been successful in some and unsuccessful with others. In philosophy, I've not been very successful.
They are asking if you want to answer your question. If you want to...
What do you think is transdisciplinary research?
This is kind of a new word for me. I'm a chemist working in biology department. That's also different from the other my colleagues who are doing purely chemistry. Because one episode I can tell you, as soon as I joined UC Berkeley in entomology department, I'm supposed to do the study of the insect, and somehow chemistry related, because after DDT we need something new, the insecticide. Okay, but I start publishing our work, because I do chemistry, cannot do the purely entomology, and most of my colleagues say Kubo is easy because he published the chemistry paper. Okay, but of course the chemistry paper, biology paper are different. We can do one reaction per day, or sometimes even 2 reactions per day. My colleague who does the ecological study, he can or she can do one experiment 1 year, per year, or sometimes even 5 years, 10 years. So the number of publication is not really, doesn't matter. But I had a hard time anyway. Okay? But when I joined this biology department, past maybe 5 years, I was really frustrated because I isolated. I lost my language, not because of English. The chemistry taught something different kind of scale. However, now I'm really feeling I'm in the middle of the treasure island. Many the projects which one scientist cannot do it. And also sometimes one campus cannot do it. Like that's the reason I try to summarize a little bit our plants. But I didn't go into the jungle collect the plant myself. I just for the supermarket or the open market, something like that. Today's science, not only economy, really global. But chemists can contribute also give the aspect from the chemical point of view. And the 1 plus 1 is not 2. 1 plus 1, 2, 3, 4, 5, even 10. So when as soon as I got the invitation letter from him, I was a little bit confused. What this means? But now I start getting understand, and really, it's difficult, easy to say that, but the accomplishment is not so easy. But the starting from here is really something. And today, actually, I'm giving the talk, but I was not prepared because I don't know what the conference means. Particularly, I was a little bit afraid. I have to discuss with him. He has been working in this particular field, he said 20 years, mine only half a year. But the purpose of this conference is to be very, very useful for particularly young scientists, because you are not learning only chemistry. When I started working in biology department, the interdisciplinary science, that's their main work. Now, this new work is coming, so the more global.
Ok, gente, mais alguma pergunta? Então, obviamente que, por favor, obviamente que eu gostaria de especialmente agradecer ao professor Kubo por ter colocado nessa fogueira. E foi essa a razão que no início eu expliquei que eu coloquei uma participação especial, porque embora ele apresente um currículo que nitidamente é transdisciplinar na nossa visão, dentro das nossas metodologias, dentro dos nossos fundamentos, mas que ele veio na incerteza e, tendo chegado anteontem, hoje já estava aqui participando conosco. Provavelmente, no final dessa permanência dele aqui no Brasil conosco, como é o testemunho do professor, levado à produção de artigos e assim por diante. Então, os nossos especiais agradecimentos ao professor Kubo por essa participação nesse momento, nessa circunstância, nessa incerteza, nessa transdisciplinaridade. Mas, obviamente, na próxima semana, aí ele já inserido um pouco mais na nossa cultura, vai poder dar a sua conferência transdisciplinar e, obviamente, disponível para as incursões disciplinares naquelas unidades, naqueles departamentos disciplinares que julgarem que a presença dele pode ser útil. Então, uma palavra final aos dois, se desejarem. Muito obrigado a vocês.